Hello, how's it going? How's it going? Guys, I'm just gonna check that. Apparently we're live already. I'm just gonna check that my audio is good. How's it going? Okay, it's good. Then, so now what we're gonna do is like we're in the second part of building applications with PINECONE. So I'm gonna share my screen on the lecture. We're gonna go to this data camp. Okay, let's listen to this.
Great work so far. Now that we've created an index and connected to it,
Thank you.
we're ready to start ingesting some vectors. Here's a series of 10 vectors that we'll ingest into our index. It's a list of dictionaries containing unique IDs and vector values. PINECONE requires vectors to be structured in this particular way, so we may need to perform a bit of list and dictionary manipulation to get to this point. Before we start ingesting these vectors, it's also important to check that they have the same dimensionality as the index. To do this, we create a list comprehension that checks if the length of the list
Checking the length of the values field in the vector dictionary from the list of vectors
under the value key is 1536 for each vector in vectors. To check that this condition is true for every vector, we can call the all function on the list. Since this is true, we can be sure that these vectors are safe to ingest. If the dimensionality doesn't match, we'll get an exception from the API. The upsert method is commonly used for ingesting vectors. Upsert is a combination of update and insert. If we try to ingest a vector ID that is already present in the index, it will get updated with the new data. If the vector isn't in the index, it will be inserted. We call the upsert method on our index and pass in the vectors. To check that the vectors were successfully upserted, we can call the describe index stats method. We can see all 10 vectors were inserted. The index fullness is still 0, as 10 is a tiny fraction of the index's maximum capacity. Note that it can take a few moments for this data to refresh, so describe index stats may not immediately show the updated statistics. Many vectors will have some form of metadata associated with them. Metadata is data about our data. This could be a date or time, a category designation, or user attribution. In our vectors list of dictionaries, it should be stored as a dictionary under the metadata key, where metadata labels and values are key value pairs. Ingesting this data into the database can be very useful. When we come to query the data, rather than having to search through every vector in the index, we can filter by metadata to only search over the most relevant records, which is much faster. We'll cover metadata filtering in the next chapter. For now, we'll ingest it. Fortunately, the syntax is the same as before. Providing that the metadata is structured as a dictionary under a metadata key, PINECONE knows exactly what to do. Let's ingest some vectors.
All right. So, okay, I'm gonna pass to hide my data camp because I'm gonna work here with the proprietary key. And now we're gonna work inside of the Visual Studio. So for this, I'm gonna first create a file that is gonna be called checking dimensionality. Oh, sorry, for checking dimensionality. And here we're gonna copy the code from data camp. And well, in this case, what we are going to do is I'm gonna copy this here, and here the method so here it says now you have you now have the know-how to begin ingesting vectors into the new PINECONE index. Okay, here's a list of vectors that I got here that have ID, values, and metadata. And then initialize the PINECONE connected to your API key. So for this, I will just put my API key in data camp. I will not do it in Visual Studio because it's already predefined in the environment. Then I'm gonna create my PINECONE index. So in that case, to create, I can go to the create index. So I can go to here In this case, this index is going to be called data camp index, because that's the instructions that they gave me. The spec, I need to import serverless spec, so I need to import this from here, and then I need to call this serverless spec here. It's gonna be located in the AWS in this region, and here's the dimensionality. So in that case, I need to make sure that the len of the vector and the field values for vectoring vectors, and we should print all. So this is gonna get me if, so first I'm gonna make cloud to cover that, and I'm gonna say for this file, please add more elements to the vector list so I can run the file. So it's gonna autocomplete this with more elements, max 5 more. Here I'm gonna run, I'm gonna copy all of this code into data camp just so I can run it there. I'm gonna run the code there. For vector in here, here's vectors. So a random model, I think is better. And here should be for vectors. So now if I run the code, so I'm going for random, I'm gonna generate metadata. So it's gonna generate a random uniform from the range. So it's gonna generate random numbers from -1 to -1. It doesn't matter, but it's gonna generate, it doesn't matter this variable, but it's gonna generate 1536 elements. So yes, that's good. That's good here. Yes, that's awesome. So it passed. Now I'm waiting until it passes here, and I'm gonna show you in my here. Now as you see, now I created this data camp index, and if we go inside of there, where I think we can check that we didn't add the records yet. Okay, I guess that if I run now, the records is gonna do here. This is Python 4, and then we're gonna see the records here. The configuration, no namespaces, no namespaces, the metrics, nothing so far. Nothing so far. What does it says? It says resource already exists. Okay. So in my case, because of the fact that this is for creating, so I don't need to create. So in my case, I need to just get this one. Okay, I don't need to even do this one because now we already created, so we just need to run it to do this because we already created this data camp index. And we're not inserting it yet, so that's why it doesn't appear there. Okay, now we're just checking the vector dimensionalities. If I do this, it should return true. Oh no, I didn't save. Okay. I didn't save, so here I'm running again. And it returned true because, you know, I forced it to make all of the vectors to have the same dimensionality as the index. She should be alright. So let's go to the next exercise. In the next exercise, we ingest vectors with metadata. So I need to initialize the PINECONE connection with your API key, connect to your index to your data camp index, and assert the vectors. Okay, so what we need to do is I'm gonna create another one. This is gonna be called 5 ingesting vectors, and in here I'm going to copy this. I'm gonna get the index from here, then index that absurd, and here I'm going to do this. Vectors metadata, so like this, import random. So I generated here the metadata, so I generated here the vectors, and then I'm gonna do this, and then I'm gonna insert these vectors here, and the ID is like the index so far. Then I'm gonna print the, in this case I think I should print the scribe index stats. So it's gonna print me the statistics of the index, but now with all of the vectors ingested. So I'm gonna do the Python. This is the number 5. Text composition are but to work given. So okay, let's go on here, and I'm gonna put it to cloud. 1 second. What is wrong? And it's gonna tell me what is wrong. Just give me 1 second because I'm asking to cloud. This absurd is the method that therefore absurd probably is wrong. I guess I need to define vectors equals to vector, something like that. Yes, it was that. So I need to do the vectors equals vectors and then save it. And then that should be it. Yes, I hear the total vector count. Now if I share you my data camp index, which is here, you are going to see that now there is 6 vectors there. That's nice. Okay, so let's go back to Visual Studio. Now we're gonna copy this part to data camp. So we pass the test. And then we submit the answer. Because of the fact that they probably had the same, now that I added this, I added 100, so either I added 94 or I'm gonna see here. Okay, now it's 100. Okay, in my data camp resource I got like 100 vectors, so that's why now if you see my PINECONE here, I have now 100 elements. Okay, it doesn't matter. We just finished this chapter, guys, and now in the data camp, now we have entered the second chapter of this course, which is gonna be about retrieving vectors and stuff like that. Okay, now I can share my screen. I can show you this data camp. Yeah, I can show you. Let's listen to this.
Welcome back. Now that we've created a serverless index with an appropriate dimensionality and abstracted our records, including metadata, it's time to talk about fetching and querying the vectors. There are two main methods for accessing vectors from a PINECONE vector database: fetching and querying. Fetching involves finding and returning a record using its ID. This is normally done to explore and verify particular records from the index. Querying involves sending a vector to the index and returning the vector or vectors that are most similar to it. If vectors were books, fetching would be like using the ISBN or International Standard Book Number to find a book. Querying is like searching for books that are similar to one we already own. We'll focus on fetching vectors in this video and querying vectors in the next video.
So with fetching, we fetch the vectors based on their ID and query retrieving them vectors to an input vector. Okay.
To fetch records based on their IDs, we can call the fetch method, passing it a list of record IDs to return. We can see the result contains a dictionary under the vectors key that contains one entry for each record returned. From these entries, we can access the vector values and associated metadata. There's also a usage key, which shows we've used one read unit when fetching our vectors. Let's talk about read units. Read units, or RUs, are a PINECONE-specific measure of the resources consumed during reading operations. Fetching, querying, and listing vectors all consume read units. For fetching, one RU is consumed for every batch of 10 records retrieved. Fortunately, PINECONE's starter account provides a generous monthly quota of read units for developing and testing solutions before scaling. Finally, we can also fetch vectors from specific namespaces by specifying the namespace argument. We can see that the previously blank namespace output has now been populated.
Wait, I was watching my phone, sorry.
Of the resources consumed. For fetching, one RU is consumed for every batch of 10 records retrieved. Fortunately, PINECONE's starter account provides a generous monthly quota of read units for developing.
Okay, so we will not need to pay until we
and testing solutions before scaling. Finally, we can also fetch vectors from specific namespaces by specifying the namespace argument. We can see that the previously blank namespace output has now been populated. Later in the course, when we come to storing and querying vectors across multiple namespaces, this functionality will become invaluable. Time to practice.
All right, got it. So, also make some tests here. In PINECONE, there are two primary methods for accessing vectors from an index: fetching and querying. All right. So, search for a particular customer review using its unique ID. This is fetching. Produce recommended news articles based on recently viewed articles. So in this case, we're gonna make comparison of proximity of the vector. So it's gonna be query. Fill films with similar plots using your favorite movie's plot. So this querying. Look up for a product information using its unique product code. So this is fetching. Okay. Now it's time to go back to Visual Studio, and this is going to be fetching vectors, and I'm gonna go into the number 7 which is going to be called fetching vectors. All right, that's good. And let's clear a bit some things here, and also here. And let's yeah, okay, I'm gonna tell you the exercise. In this exercise, you've been provided with a list of IDs containing different records, and I'm gonna, oh, this is number 6. I don't know why I put 7. So I'm gonna do this. Index. Okay, here's the description. In this exercise, you've been provided with a list of IDs containing IDs of different records in your data camp index. You will use these IDs to retrieve associated records and explore their metadata. Okay, so let's copy this here. We don't need this random anymore, because now we're using already the database that we have in our PINECONE. So we're gonna, from the Python client, we're gonna import the data camp index. Yeah, and then fetch the vectors. So we are gonna do index.fetch, I assume, and this is gonna be IDs equal to this IDs, and fetch for and we're gonna get the metadata from those ones. So from the fetch vectors, give me 1 second, I need to understand. Okay, but if I get the fetched vectors, I need to, okay, you know what, let's inspect this. Let's inspect that one. Python, this is gonna be 6. Until this part, just to know what is gonna print there, and then from there we can move on. So from there, we need to get the vectors, and then here's gonna be the ID, and here I need to, from the vector, I need to get the metadata. Okay, so then I can run it again. Now I should see only the metadata. Yeah, here the metadata of the 3 of the ones that are required. So now it works. It's good. Now we're gonna paste this into data camp, and in data camp we also need to paste the API key, and let's run it, and let's submit it. Good, it worked. All right, and now we are gonna have another lecture. So we are going to show this from DataCamp. So let's go.
Aside from fetching vectors, we can also query them. Recall that querying involves sending a vector to our index.
Wait. Okay, that's good.
And receiving the most semantically similar vectors in return. Querying is used in all kinds of AI applications. In chatbots, user prompts can be embedded and used to query a vector database and provide the model with more relevant information. In effect, it gives the model more context than it had from its training data. Similarly, in semantic search engines, user searches are embedded and used to query the database to return the most relevant results. We can use the query method to query the index. We need to pass it a vector to query it with, and the top k argument, which is the number of results to return, the top k most similar vectors. As with other index methods, the query vector will need to have the same dimensionality as the index and other vectors in the index. The output shows the IDs of the records with the most similar vectors. Each record is also given a score, which is a measure of the vector's similarity to the input vector. The vector values aren't shown by default for brevity. To return the vector values in the output, set the include values argument to true. Notice for both of these queries, we consumed 5 read units. Querying, like fetching, also consumes read units. For querying, calculating the number of read units that will be consumed in an operation is less straightforward than for fetching records. The number of RUs is dependent on the number of records in the namespace being read, and the size of the records, which is itself dependent on the dimensionality of the vectors and the amount of metadata stored. PINECONE provide a guide on the number of RUs consumed for different configurations, but if these numbers don't reflect your project, I recommend taking a deeper dive into PINECONE's documentation linked here. So how does the query method actually determine the most similar vectors? What happens is that we compute the distance between the query vector and vectors in the index. And the vectors
just in case we did cosine similarity, but with Chrome DB, so the concept is basically similar.
Smallest distance are returned. There are different metrics for calculating the distance between vectors, with the cosine similarity being one of the most common and the default in PINECONE. There's also the Euclidean distance, which is essentially a straight line distance, and the dot product. Determining the most appropriate distance metric can require some experimentation. The distance metric is set when creating the index using the metric argument, and can't be changed afterwards. The argument can take the strings cosine, Euclidean, or dot product. Time to give querying a go.
That's awesome. So now let's hide our DataCamp. And now let's go into the Visual Studio, and in here we're going to return in the most similar vectors. So it's gonna be querying vectors. It's gonna be like this, and then I'm gonna pass the description here. I'm gonna comment this. Okay, it says querying vectors is a foundational to so many applications. It involves embedding a user input and comparing it to the vector in a database and returning the most similar vectors with a mystery vector called vector, and you will use it to query your index called DataCamp index. Okay, so what we need to do here, this is the base code that they're giving us, and in here what we need to do is like query, and in here we need to pass several properties. One of the properties is vector, that is gonna be vector, and let's take a hint. In the top k we're gonna do, because we need to return, we need to retrieve 3, so it's just 3, and yeah, that's pretty much. I think if we do this here, and then we're gonna first run it in DataCamp just in case. Yeah. So if I do Python 7, yeah, it should print the two most similars. But the question is, no, it's not right because I didn't save the 7. So I'm gonna clear this Python 7. Now that I save it, now it's gonna tell me where is vector, and I'm gonna copy relative path for this file. Please create a vector. It's gonna be a vector variable, so I can run the file. Let's consider dimensionality of. Let's go into the data camp. Because I need to check what is the dimensionality of this data camp index. Give me 1 second, I'm trying to figure out how can I get the I think it's this 1500, because when we created this in just in the vectors, yeah, it was this 1556. So it's gonna create a random so I can run it there. Yeah, it's gonna create that, and then I can run this good. And this is 7. So now I will create just a random one, and I will get 1 vector. So that is good. Now let's go into the next exercise, which is going to be it's called changing distance metrics. And in this case, what we want to do is like changing the database to calculate the distance, not from the classic, which is the cosine distance, but in this case we want to change it to the dot product index. So for that, what we are going to do is gonna create a new index. In this case, and this is going to be like this. And this is gonna be called dot product index. The metric is going to be dot product. Then here when we print, we need to print the index describe index stats. Then we do this. We don't need this random. We can remove this. So now we run this 8. Now we when we see the stats, it's gonna show that now this is the metric. Should show. So because I didn't return here the index. Okay. Index. So I will save this here. It should be in the 8. What it says? It already exists. So if it already exists, it means that this was my issue. So now what I need to do is, instead of doing this, I need to get this index now because it was already created. So I'm going to do the here. This is gonna be called first creation, and now I will get the index because it was already created in the first run. So yeah, see there, the metric is the dot product now. It has no vector yet, so it's good. So now we need to, now we're just gonna copy this here. Now we're going to paste this here, and then we're gonna do this here. Okay, so I'm gonna run now this into data camp. Because in data camp I didn't put the key. 1 second, I'm gonna paste the key there. Run. What do you mean? Okay, give me 1 second. It's not running good in data camp, so I'm gonna reload the page only. I just want to make sure. Give me 1 second because I just want to make sure that it runs, and then I'll come back here, to Visual Studio. Why does it say that describe index stats is not? Explain the error. Because in my local, the describe index stats is working, but in the cloud it doesn't. Because when I do the create, it doesn't return nothing. Alright, so I should just do the PC list indexes. Alright, because so just in case when I do this function PC create index, it doesn't return nothing, just in case. Okay, good. Metadata filtering. Okay, guys, now let's take a break. I'm gonna go take shower, walk the dog, eat, and then we're gonna come back with the third part of the streaming. So see you